In this video, we're going to introduce related rates problems. Related rates occur when you know several rates of change and want to use them to find the rate of change of some related quantity. A classic example of related rates is this. Someone, let's call him Bob, leaves a building at a fixed time, let's say 7 a.m., and walks due north at some fixed speed, let's say 3 miles per hour. Alice leaves the same building at the same time and walks due east at 2 miles per hour. So 3 miles per hour and 2 miles per hour are both rates. And now we'll ask a question where we need to find a third related rate. Assuming they maintain their speeds and directions, how quickly are they moving away from each other at 9 a.m.? We'll solve this problem, but we'll first make some general suggestions. I'll say up front that related rates tend to be difficult for everyone. For me as the professor to teach, and for students to learn. And that's because there's no hard and fast rule for solving related rates problems. Each problem has to be taken on a case-by-case basis. That being said, the textbook does recommend, and I agree with this, that we should try to follow a set process. Draw a picture, label everything that seems like it might be important, write down the numerical information, write down what we're trying to find. 4 is always the tricky one. Write an equation relating the variables. Differentiate, and this equation is usually going to be an implicit equation. So that will be implicit differentiation, and then evaluate. And just seeing this list probably doesn't help us much. Let's go back to this example, and let's try to work through it using that list as a guide. So again, here's the problem we're trying to solve. Bob is walking north at a fixed rate. Alice is walking east at a fixed rate. We're interested in how fast they're moving away from each other. And the first piece of advice is to draw a picture picture and label everything that seems like it might be important. Okay, so here's our building. Bob is walking due north. Alice is walking due east. And of course, as Bob walks north and Alice walks east, the lengths of these line segments change. Bob's walking north at 3 miles per hour. Alice is walking east at 2 miles per hour. So since we're interested in rates of change, and this distance and this distance are changing with time, let's label both of those. What we're ultimately interested in is their distance from each other. So let's label their distance from each other as well. Now that we have a picture, write down numerical information. What numerical information are we given? Well, we're given rates of change. This is a rate of change, and this is a rate of change. And rates of change, of course, are derivatives. So we're told how fast this is changing. We're told this distance is increasing at a rate of 3 miles per hour. dB dt is constant. Bob's walking north at a rate of 3 miles per hour. We've got this constant rate of change. Likewise, Alice's distance from the building is increasing at a constant rate of 2. There might be other stuff that interests us down the line, and we might have to come back and try to figure out some additional stuff. But this is the only numerical information we are explicitly given. So for now, let's move on to 3. What are we trying to find? We want to find how quickly they're moving away from each other at 9 a.m. Their distance from each other is d of t. The question of how quickly their distance from each other changes is a question about derivatives. And we're interested in the derivative at a certain time. T here, I guess I haven't explicitly written this down, but it's the number of hours since Alice and Bob started out, since 7 a.m. So 9 a.m. is 2 hours later. Hence T equals 2. Now 4 is the part where the formula breaks down and you have to approach each problem on a case-by-case basis. We're given information about A and about B, and we want information about D. So according to this guideline, we should relate to the variables we have information about, A and B, to the information we want. Sorry, to the variable we want information about. So how can we relate A and B and D? And here's where we sit and think. And maybe we try some things, they don't work. We try some other things. There's no one size fits all way of doing this. But what we may eventually see is that this is a right triangle, and we are trying to relate to the legs of the right triangle to the hypotenuse, and there is a very famous way of doing that. I'm referring, of course, to the Pythagorean theorem. Now that we've related the variables we have to the variables we want, we differentiate. I mean, remember what we want here. We want a rate of change, and a rate of change is a derivative. So differentiating will introduce derivatives, which we need to do. As I warned you about when I wrote this down, this is implicit differentiation. A and B and D are all functions of time, So when we take the derivative of this, a of t is the inside function, the square is the outside function, and similarly here, b is the inside function, the square is the outside function, d is the inside function, the square is the outside function. So the chain rule says to use the power rule as usual. Heck with it. Let's just change notation. Use the power rule as usual, but then multiply by the derivative of the inside function. Questions like, what is the derivative of the inside function? We'll leave for later. For now, let's just take these derivatives. And we can do some cancellation just to simplify stuff slightly. There's a 2 and a 2 and a 2. And we can divide both sides of this equation by 2. And we get this. We should be at our last step, which is to evaluate. And what I mean by that is that we're interested in some specific value of t here. T equals 2. So we'll let t equal 2 and see what happens. A of 2 times a prime of 2 plus b of 2 times b prime of 2 equals d of 2 times d prime of 2, and this is precisely what I want. So, good news, bad news time. A prime and b prime are known constants. A prime is 2 always. B prime is 3 always. The bad news is that we do not have A of 2, B of 2, or D of 2 written down anywhere on this page. But I thought something like that might end up happening. When I was writing these down, I said, these are the only numbers we're given, but we might end up having to come back and find some more. Bob is traveling at 3 miles per hour. If he travels 3 miles per hour for 2 hours, B of 2 equals 6. If Alice travels at 2 miles per hour for 2 hours, A of 2 equals 4. D of 2 we can find using this equation. 6 squared plus 4 squared equals this value squared. This works out to be about 5 point. Sorry, looking at my. No, it doesn't. I entered something incorrectly into my calculator. D of 2 is about 7.211. So now A of 2 is 4. 4 times 2 is 8. B of 2 is 6. 6 times 3 is 18. Equals 7.211. That's a D of 2 times a D prime of 2. Finally, we do this addition, we do this division, plug it into our calculator. About 3.606 miles per hour is the speed at which Alice and Bob are getting further away from each other. In this video, we've done a related rates problem. Unfortunately, as we've said, there's no one-size-fits-all solution to these. We'll see a few more examples, and each of them will be quite different.